Alright guys, so as you can probably figure out, we're having to go ahead and change our order of lessons a little bit. And the reason for that is I want to make sure that we're giving you kind of the most critical concepts out of Principles of Engineering that'll help you proceed on into your other classes. And projectile motion is a great one to help get you ready for whenever you take your physics classes, because this is something that they'll touch early on. And it's also giving us an opportunity to go back and look at free body diagrams a little bit, how we can handle our calculations, especially with concepts like trigonometry, because we're going to be thinking more than just velocity. We're going to be thinking about the acceleration that goes with us, which is one of the things that I alluded to back at the beginning of the course in simple machines. And I said I didn't want you to have any projectiles because you need a special type of math to deal with those. So what we're going to look at is a couple of different scenarios, and the first is going to be what's going to happen in a skydiver. So a skydiver, we know, is going to go straight down. Okay, we're not going to consider left, right, lateral motions. We're just thinking about the acceleration going straight up and down. So to get us started off, a few key terms. First is speed. Okay, you guys should remember speed is the distance a object is traveling over a unit of time. Miles per hour, feet per second. One that we'll see a good amount in this class is either the feet per second or the metric equivalent, meters per second. And then you should also remember velocity, whereas we're taking that speed, 60 miles per hour, but we're also including a direction. So 60 miles per hour going east, or 10 meters per second going down, or accelerating at and then acceleration. Of course, acceleration and velocity not exactly the same thing. Acceleration is the change that's happening to that velocity over a period of time. So accelerating to 60 miles per hour, we may be getting an extra 5 miles per hour every second that's passing. Okay, and that's going to be important when we start looking at one of the main forms of acceleration and gravity. So we know that gravity tends to pull all objects towards the center of the Earth, and that's actually generalized for us in the situation that most of you are going to be used to, and that's being on Earth. But we've alluded to how every object, a person, the moon, the sun, the computer that's sitting next to you, everything that has a mass has some amount of gravitational pull. Okay? But in most cases, it's not enough to be worth too much. We think about like the International Space Station. They've got Earth's gravity, the moon's gravity, the sun's gravity, all of it's affecting them. And while they're not in zero gravity, the distance from those objects is far enough that there really is nothing, really practically speaking, nothing that's really going to act like gravity the way that it does on Earth. So because we're here on Earth, we have gravitational acceleration, and that's a constant. It's going to apply to any object. Doesn't matter if it's an elephant, or if it's a peanut, or if it's your cell phone. Okay, any object that falls, given free travel, is going to be accelerating towards the Earth at negative 9.8 meters per second squared, or it's going to be accelerating at negative 32 feet per second squared. Those are both rounded off values, but those are the ones that are in the Project Lead the Way formula sheet, and they're good for most of the calculations that you're going to be doing. So let's talk about how that acceleration works. The moment that you, the skydiver, gets out of the plane, you're still effectively at the same altitude as the plane. Okay? And up until the moment that you've left out, the lift of the plane is being applied to your mass as well. But the second that you free yourself from the plane, that's where the gravitational pull has nothing counteracting it. So you start out at 0 feet per second, but after 1 second, you're now traveling at that 32 feet per second. Okay? That's your velocity. But you're accelerating increasingly as you continue that time free. So at 2 seconds, you're actually going to be at 64 feet per second squared as a velocity. You're still accelerating at the 32 feet per second squared, but that continues. So every second you're getting another 32 feet per second added to your velocity. So 96 feet per second. At 4 seconds, you're up to 128 feet per second. At 5 seconds, 160 feet per second. 6 seconds, 192 feet per second. Okay? That acceleration is staying the same. Now, in more advanced lessons, we would go more into terminal velocity. It's a concept that when we look at the free body diagram, the orange dot, we have the gravitational force, the force, the acceleration due to gravity that's going to be pulling you down at a constant value. But at some point, that acceleration is going to stop because there's going to be enough drag, enough resistance from the wind or the position that you're in that's going to go ahead and counteract that new acceleration. You will still have a very fast velocity, something like that 192 feet per second squared. But that terminal velocity, that constant speed that you're going to be falling at, will remain the same unless you're changing your position, changing something about the drag that's being applied. That's more of an aerospace question. It's something that gets into physics, more traditional forms. But it's worth recognizing that not everything will fall at the same rate. Okay, and there's a traditional saying. Sir Isaac Newton went ahead and dropped in a bowling ball and feathers at the same time, and they both ended up at the same place at the same time. And in an ideal universe, okay, or as you can see in this Brian Cox video, if you have a pure vacuum and there's no air to go ahead and provide resistance, you're going to be able to go ahead and see that a bowling ball and feather will fall at the same rate, even though their masses are obviously different, their shapes are obviously different. Whereas when they have to deal with Earth's atmosphere, okay, that feather is going to sway around in the wind because it has a much lower terminal velocity than a perfectly round bowling ball would. So it's a fairly short video, but it's a cool one to go ahead and watch. Definitely encourage you to check it out. But what happens when we start dealing with more than just one axis, when we're going more than just left or right, or up or down? And that's when we've got cannonballs, okay? Specifically human cannonballs. And this is where we actually get into the projectile concept, okay? So recognize that a projectile is any moving object upon which the only force acting upon it, okay, the only active case, is going to be gravity, okay? It will have drag in theory, but we're going to negate most of that. And gravity should be the only thing that's really kind of focusing on this. And for the sake of simplicity, we're only looking at the gravitational pull of Earth, okay? So what we were going to start caring about, okay, and where that trig becomes important, is we're going to include a firing angle, okay, basically a measurement in degrees from the horizon that is elevated for it to go ahead and project into the air some amount, okay? And we're also going to have an initial velocity, that initial kick that it gets out of the tube that it originally carried it. So whether it was a bullet or if it's that human cannonball, okay, the angular speed of that, okay, is going to affect how far it actually goes and how long gravity can actually be influencing it. Now remember, we've got the theta, one of the symbols that we've gotten used to seeing when we're talking about angles, and we're also seeing the initial velocity, okay, v with a subnotation of I. Now in this case, rather than jumping out of the airplane, we're shooting straight up, okay? So we are eliminating any left or right actions. We're only assuming that it's going straight up or down. So what happens is, if we go ahead and have that initial velocity of 128 feet per second going straight up, after 1 second, gravitational pull is starting to pull downwards, okay? After 2 seconds, that gravity has continued pulling down. Okay, so you're now down to 64 feet per second. At 3 seconds, you're down to 32 feet per second. At 4 seconds, you have this moment where you're not feeling any forces applied to you. Okay, it's where you throw a ball up into the air and it stops for a fraction of a second. And that's that zero acceleration. It's just floating there. But as time continues, since we don't know how to stop time, that acceleration due to gravity continues pulling you back down towards Earth. So as the force of gravity due to Earth goes ahead and continues pulling you back down, that moment that you were at 0 feet per second, well, you're now headed back down towards Earth. So rather than going up at 32 feet per second, at 5 seconds, we're now traveling back towards Earth at 32 feet per second. And we continue accelerating until we get back to where we started off. And this is the point where you took off at 128 feet per second going upwards, you're now going down 128 feet per second, which means the sudden stop at the end will definitely hurt. Okay. So what happens when you approach this vertically? Well, we still have to remember that the velocity, okay, the direction is going to matter. Okay? You can try and shoot something straight across, but we know that gravity is not affecting left or right movements. Okay? It's affecting up and down travel. So what actually happens is, even though your horizontal velocity is going to stay the same, that 128 feet per second to the right, you're also going to be going down 32 feet per second. Okay? And at 2 seconds, you're still going 128 feet per second to the right, but you're now going 64 feet per second down. Okay? And that continues until other forces are going to slow you down. Friction, resistance, things like that.